Testing. All right. Now we're live. Okay. Um, don't you just love change-ups? We are doing something completely sort of different today. Next up on the engineering track is dynamics. I promise it's coming. But in the meantime, in the most recent episode, we had taken a brief tangent to look at a front-end challenge on DevNet 2 about rendering solar systems. And we got to the point where we could have 3D planets in a Three.js based app. It was pretty neat. We were not to the point where we had satisfied all the requirements of the challenge. Um, I went back and looked at some of the inspirations for that challenge that they had listed in the site, and lo and behold, one of them was actually based in Three.js. So I didn't want to get anything too close to them. And so in addition to getting across the finish line, we're going to see sort of what we can do differently. This was a little bit more graphics and shader oriented, so we'll focus a little bit more on like the modeling, right, and the coding. In particular, we want to be able to present a 3D view of the solar system that requires a knowledge of where the planets are in the solar system. So if you look at the, if I pull it up here, what had we done before? Front-end challenge. So here's the markup, right, that had been presented as part of the challenge. And if you look at the information for this markup, it's not just textual, but even the numeric data, distance from the sun. Okay, maybe you could parse some sort of radius, right, some major axis. Orbital period is actually the same thing, believe it or not. If you know the same major axis, and I think we had walked through this at one point, the orbital period is purely a function of the same major axis. Speaking of which, this is a good excuse. You'll notice the monitor is no longer jiggling. That's because we're no longer drawing directly on the screen. We have a tab now. Hopefully this is less relevant for today, but hopefully it will be useful for some of the engineering content. So anyways, we have this gravitational parameter, which is basically big G times mass of the central body, right? A cubed divided by that gravitational parameter. A is the same major axis, so basically radius of the orbit. And the square root of that times 2 pi gives you the period of the orbit. So if you know nothing more than that, then you can actually figure out this. And then that's actually not enough, right? That's purely, if you want a flat circle, fine. You have a radius for the flat circle. But this seemed like it's an interesting opportunity to do something a little bit more complicated than that. We're going to actually compute within sort of the inertial heliocentric frame, as it's called, the coordinates of the planets in real time. So how do we do that? Well, fortunately, we're going to walk through a great exercise, which is taking an interesting algorithm from a textbook and implementing it in software. In particular, this is Orbital Mechanics for Engineering students, a fantastic textbook. Other people prefer Velato. There's all sorts of different resources you could look up online, etc. But there is a, let's see if I can find it, Chapter 8, planetary frames. Here we go, 8.10. And this will help us learn a few interesting lessons here. In particular, what we're going to use are a table of values here, and you can see it's a little bit more sophisticated than just the radius, right? So we'll walk through exactly what these mean and how to use them. First, we're going to transcribe them, though, into our project here, just so we have a captured version of that. And spoiler alert, I've typed this up beforehand. So that is from a very interesting paper. Actually, let's see if we can find it. This might be Google Scholar. Standish. 1992, I think. Here we go. I believe this is the right one. Let's check it. So yeah, this is an interesting derivation. Basically what the model comes down to, and here's some of the parameters and how they compute them, the reference stars that they use, and finally this table here, which is in slightly different units, but basically a transcription of that is what Curtis had in the textbook. So we have 6 elements here. You'll notice they're not quite the traditional Keplerian elements that we might use for a satellite, but they're similar. And they're given in units and drift, like a rate, units per century. So these are evaluated at J2000, basically noon of January 1st in the year 2000. and we can use the time offset. It's sort of like linear fit, right? So if the inclination was here at J2000 and, we're trying to evaluate it 5 years later and the drift was 10th of a degree, that's obviously exaggerated per Julian century. Actually, that might be more accurate. We can do an estimate of linear fit, right? And come up with the elements at a particular point in time, because it's not purely what we call restricted two-body. These forces, the planets are acting on each other, and the sun is not, perfect sphere, and so these orbits are not constant. But that gives us a very good estimation, at least. And if you wanted to do something higher fidelity, you would go off and pull up like the actual kernels from JPL and do like 10th order polynomial or 17th order polynomial interpolation. But this is good enough for us today. So we will take that JSON, and that will be our starting point. Standish catalog. So you can see here, this is, again, just what he had in the textbook. We're just transcribing the JSON here. So we have semi-major axis, eccentricity, inclination, right ascension, ascending node, longitude, perigee, and mean longitude, and then we have drift rates in seconds for these angles. That's like degrees, minutes, seconds. It's specifically, those are seconds per Julian century. So every 100 years, that's how much it changes. And that's the rate that we'll use to come up with these elements. So that's great. But that's not actual code. Like, how do we do this, right? So we're going to put together a JavaScript package. This is going to be let's see. If I remember the shortcut here. Oh, we're in PowerShell. Who uses PowerShell? Here we go. All right, so we have a package. Single file JavaScript package that basically has one job. Given a particular time, tell us in the heliocentric inertial frame where the planets are. And then if you remember the previous app that we were putting together, that will be enough to update the position of those planets at any point in time purely by using this package. So there's a few dependencies we're going to add. I've gone over some of these in articles, but not really on, let's see, a episode video here. So we're going to consolidate some useful packages here. This will serve a double or triple purpose. It's a sort of demonstration of how to do quick and efficient JavaScript packages. So there's some development dependencies we're going to use for testing and coverage. And then we don't actually have any runtime dependencies. This is going to be purely self-contained math and all that. So let's add get ignore. That's not how we spell ignore. All right, we don't want to include no modules. And we'll keep the lock valve for now. Need to initialize a repository. We're good. All right. So nothing here yet, right? Empty package for all intents and purposes. So let's add, we're just going to do some self-contained calculations. So we only need one file here, and we're going to put all this stuff together. So since we're putting it all together, you can imagine, and on a solar system scale, it's actually kind of useful to do kilometers. Use gravitational parameters, module constant. So I mentioned this technique of just taking an algorithm from a textbook, walking through an implementation. Curtis is particularly good about enumerating how those algorithms are defined. They can be a little bit recursive. Well, maybe not recursive, but you need to expand them, right? Because a lot of these steps, find the right one here, non-hominid planet, there we go. So here's the algorithm. If I can mix up the sides right? Algorithm 8.1. A couple of steps, including some that reference some other algorithms that we may or may not go into some degree of detail. So let's see. We first need to, we'll start with our high-level entry point, break down the dependencies, and flesh those out. So first, what do we want our main entry point to be? We want to get the position and velocity from those elements and a particular date time. So we'll pass in some representation and some particular date time. We'll say that's going to be an object. A for JS.doc, and this will be a date. And it's going to return an array. So this is going to be a 2-element array with position and velocity in heliocentric frame. These are in kilometers and kilometers per second. So each element in this array will be an array of 3 numerical values, right? So it'll be like 2 3-dimensional vectors. So let's break out the steps here. So the first step is calculate Julian day number, JD. And then calculate T0. This is number of Julian centuries from the epoch of our states. We need to calculate the elements based on that date. And we need to, let's see, step 4, compute angular momentum h. So what is it? Compute from semi-major axis and eccentricity, which we'll both get from the elements. Next, argument of perihelion. That's basically omega equivalent. And mean anomaly. From, let's see, bar, we'll call this, what should we call this? W bar. And omega right ascension and longitude. Okay. Next, solve Kepler's equation to get eccentric anomaly. Kepler's equation is a transcendental equation, so we have to solve it numerically, but there's well-established methods for doing that, basically just Newton codes. From eccentricity and mean anomaly. Then compute true anomaly from eccentricity. We'll call that theta. And then we'll have, at that point, we'll have all the elements to compute the position and velocity from angular momentum, eccentricity, argument of, or right ascension and ascending node, inclination, argument of perigee, but really it's perihelion, because we're in the solar frame, and true anomaly. So at this point, these are well-established algorithms. We'll be able to rely on a few other implementations, and in this case, even Curtis says, go back to algorithm 4.5. So how do we break this down? So there's going to be a lot of functions these are going to call, and we're also going to need a lot of utility like helper functions, right? And I may end up pacing all this because it's like 13 minutes in already. So for Julian day from a date, we have to be careful with don't need too many helper methods, but we do need to be careful with how JavaScript in its wonderful glory indexes months from 0. The difference between days and dates. And making sure that we're evaluating in UTC. Seconds is also an integer value, so since it computes milliseconds separately, we're going to add that. Now we can say get this is the Curtis algorithm from dateVec. So our dateVec in this case is just the Julian day number, not the Julian day value. Number is just the integer value of days from the Julian epoch. We need a universal time. And of course, all these functions are things that we'll implement. This is a decent software engineering technique where you start at the top and you figure out what you need, and then you work your way downwards, sort of recursively expanding, and then you implement up from the bottom, right? You figure out, what do I need to call, what do I think might be reusable, or at least nicely encapsulatable. So from the Julian day number and the universal time, we can get a Julian date value, so the floating point equivalent, and then we can get Julian centuries to use for the elements, right? So we have a couple of functions we'll need to define here. We're going to go ahead and export everything because we want to subject it to unit tests, and unit tests will just call what's exported from the module, evaluate it externally. So what did we define here? YMD time vec H MS, assuming I can not make any spelling mistakes, of course. From date time, J0 universal time. All right. So that's sort of scaffolds for those functions, right? Now the question is, do we want to go breadth first or depth first? Implement them now or continue to expand? I'm actually going to continue to expand the sequence because you never know what you might want to reuse further on down the call chain, just by adjusting the call interfaces a little bit. So once we have all those things, let's assume that we've implemented it, right? But useful to make sure we can convert. There's a lot of degrees and radians conversions here. A lot of the constant values we're referencing are in degrees, and the actual math functions we need for sine and cosine, and are in the JavaScript ecosystem at least, are in radians. So we'll want to convert those. We'll also be converting in the table. Those semi-major axes are defined in astronomical units. So basically, you think that's like how far away the Earth is from the sun, right? But it's a specific distance, just based off of that approximation. So we will see 78. Need to convert those measurements into kilometers. Okay, so now we can start interpolating, right? So we actually did this. Let's see, what do we say? T0 here. This is here. So we'll have a method to interpolate those elements, or I guess it's extrapolate, right? From that structure. And again, this is why we defined it in JSON instead of CSV. We don't need a CSV parser for it, but we'll also be able to say, okay, we know this structure has this particular schema. Let's put this over here, in fact, and we can reference it. So just for a little bit, AAU times our conversion factor, and did I not spell that correctly? No, I did not. Planetary orbital elements. Go away. Nope. This will be CD. Yep, that's how we defined it. Again, in this particular case, we'll want to convert it. And then those rates are all expressed like so, right? So basically, this is just a function that takes m and b and x and computes y, right? So it doesn't need to be too fancy, and more to the point, it doesn't really care about what you're computing. Technically, right, this is bmx because m is the rate. And not surprisingly, that will be pretty straightforward to implement. But more to the point, we can go ahead and replicate this to interpolate all of the things that we think we will want to compute. We don't need to convert eccentricity. That's unitless. Let's see, what do we call that? DE 0. What's next? Inclination. Internal representation, we're going to use radians. So of course, need to multiply that and convert it. let's see, d inc degrees. Actually, it's d inc seconds, isn't it? Okay, so that's what? 60 seconds in a minute, 60 seconds, or 60 minutes in a degree. So we need to divide that by 3600. And then convert the decimal degrees to radians. We will also want, oh, that's right, to wrap this or modulus it into 0 to 2 pi range. Always helps to constrain ranges, but in this case, this is actually kind of annoying because if you go into JavaScript and you say, 1.2, great, but if you do that, it doesn't round to 0 to the range of the modulus, it rounds to minus to plus range, right? So we'll want sort of a helper function here. We're going to call it posmod, and it just takes, some x and returns within the range of 0 to big X, right? So we can use that here to say posmod, and then 2 times math pi, and then we know our answer is within that range. So we'll need to do that with all of the angular measurements. Inclination, right ascension of ascending node, which we say here is ran degrees, so, and then d ran seconds. Let's see, lop, longitude of perihelion, right? And looks like that's in degrees, d lop seconds. And let's see, what's next? Mean longitude. Okay, I think we're good. All right, so now we have some of the elements. Next step, we need, let's see, kilometers squared per second to compute angular momentum. We'll have a helper function for that. Same major axis and eccentricity. Argument of perihelion from longitude and these don't actually have their own elements or their own algorithms. This is just, and you can go through the derivations for these. You can, backing out angular momentum in particular is pretty straightforward. In this case, this is an interesting variation on sort of the orientation of the plane, is all it's really doing there. We need argument of periapsis, mean anomaly. Get from mean longitude and longitude of periapsis. So we said that was ML to distinguish mean anomaly, and then longitude periapsis. All right. So that's actually enough for us to see. What did we say? Yep. Start solving for Kepler's equation. Let's see. So we have a couple of helper methods we'll need to define here. Longitude and longitude of periapsis. All right. That's enough for us to solve Kepler's equation. That's a pretty, as I mentioned, a pretty well established algorithm, but it is numeric, So let's define an algorithm for, or a method for that. The result is the computation of the eccentric anomaly from mean anomaly and eccentricity. You'll probably notice there's a naming scheme going on here in the functions. And then once we have that, we can compute the true anomaly. There we go. All right. So we have a couple more helper methods here. What do we call that one? True anomaly from centric anomaly. It's a E. Brand E. This is a decent trick, or at least, casing arguments being what they are across languages, especially for engineering computing, I find it very helpful to use both. Basically, a camel case for the name of the variable, and then underscore sort of snake case the units, right? So you never lose track of what the internal representation of those units are, or for that matter, at the interface. Most you can represent in one character or two, kilometers, for example. Rad just helps to make sure this is actually radians. And then there are useful ways to combine those. Let's see, where's an example? We had a rate up here, right? Oh, seconds here. Kilometers cubed per second squared, right? It's fairly deterministic. There are some places where it can technically have multiple interpretations, but it's nice to have some sort of mechanism to make sure you don't forget people looking at your code and know exactly what the units are. Okay, so now we need what are called, let's see, actually that's that. Boom, boom, boom. Okay, so this is going to take place in several stages. Once you know the elements of a particular orbit, basically you have the parameters for an ellipse and a location on that ellipse. But you also need to take into consideration the orientation of that ellipse, because tilted, etc. It's oriented this way with respect to which part's narrow and which far away. So first, it helps to evaluate position and velocity within what we call the parafocal frame, which is specifically the plane where you're like the orbital plane, x, y, and then z is out of the plane, where negative x is toward periapsis, positive x is towards apoapsis. And then once you have what are basically 2D coordinates, you can apply frame transformations for the orbital plane. So it's a 3-1-3 rotation of the plane about the vertical axis, and then it's tilted about the x-axis, and then within that plane, the orientation of basically the periapsis, right? What the shortest point is to the ellipse of the orbit. So first, in this case, PQW are the coordinates in parafocal frame, as we call it. So we'll compute those. And we can compute those fairly easily from angular momentum, eccentricity, and true anomaly. Same thing with velocity, but of course that's in kilometers per second here. And then we can convert, so compute parafocal, convert to the heliocentric inertial frame, which is what we really want. This is not technically ECI. ECI stands for Earth-centered inertial and is somewhat poorly defined, but the transform is the same. We're going to get a matrix that converts from one to the other. Of course, we're not using a linear algebra library, so we'll be doing all these things. We'll have a few helper methods that we'll test rigorously that just do these things with arrays. Alternatives could include Sylvester, or you could reuse the 3JS numeric types. Those are all useful, legitimate things. Right now, we're just trying to keep this self-contained is all. And we're going to multiply matrix by a vector to convert those. Did I get that right? Okay, yep, go. parafocal, and now we're ready to return those pairs of arrays. Okay, so a couple of helper methods we're still missing out here. Multiply matrix by vector. Yep. We need to compute the transform from the parafocal frame. That is CRAN, inclination, and argument of parity. Again, that's just a 3-1-3 rotation. We'll concatenate. RV and parafocal. This is practically a straightforward calculation. H, E, and theta. Let's just borrow these definitions quick. There we go. And as it turns out, very similar implementation. Identical interface, right? Okay. So we have our implementation at the top level now. We did this breadth first search. We can go through and identify like what other helper functions this module might need. Let's see, do we want to do all that? Yeah, I still want to talk about testing. We're already at 31 minutes. Okay, so JS talk is helpful. You can go in and define exactly what the interface is. G00 from DateVec here. These are mostly equations from the Curtis text. JD from datetime. Julian centuries. Current elements. Angular momentum. AOP. MA from ML. Yeah, because you really want to talk about testing. Okay, so this is the interesting one here. This is the one that solves Kepler's equation, right? So you can tell a little bit more numeric. You have some estimation, you're computing a value of a function as you try to find that root and slope towards that root, offsetting it. Classic Newton codes, right? Or Newton Raphson. Uh-oh, no, I can't remember. I'm getting mixed up. Good. Okay, true anomaly from centric anomaly is just a tangential transform, inverse tangents of tangent. And then here's the fun stuff, right? So z coordinate in parafocal frame is 0, of course, because by definition we're within the frame of the orbit. And it's for, let's see, we need, is this right? Yeah, okay. There's angular momentum squared over mu to 1 plus e. Yes, okay, good. There we go. So it's not a circle. It's a cosine of a cosine. It's a word for a second that my testing had lost something. Velocity is very similar, only it's e plus cosine, and then of course it's tangential, right? With that skew. Okay, now we need some linear algebra stuff. So we're going to take a few rotation methods for generating rotation matrices. So you can rotate a vector, right? Or you can define a frame by which the vector is reevaluated. So basically the opposite direction. So we differentiate that with lowercase r and uppercase r for 1 and 3 axes, respectively. We're going to need a dot product function. So what is the value of some vector, dot product times some vector? We're going to need, let's say we already talked about top level multiplying a vector by, or matrix by vector. Again, these are all just assuming like array types in JavaScript, right? We need matrix multiplication because we're going to be concatenating rotation matrices. I did not spell that correctly. So in this case, we'll define different rows, define different columns, and then get the dot products of each of those in different combinations. Okay, pretty straightforward. And then to get that matrix, I think we skipped one here. There we go. Let's move you down. And multiply it, or it's R3, R1, R3. Yep, okay. And that's backed out because it's in the opposite direction. So far, so good. All right. It will help. Since that's a rotation, we'll need to transpose it. So I have a matrix transpose function here. I don't think we assume it's square. Yeah, we don't assume it's square. Oh, I missed one. Good. QPQTCI. It's the same one, but it's not this implementation. This is actually the other way around. Here we go. With identical parameters. Right. Here's where the transpose comes in. Okay. There are a few other things. If you look at the algorithms in Curtis, some helper methods that come in handy here. Things like determining the integer portion of a number, sort of floor, but it can depend on how close it is. We need what UT from datevec. So given time, basically decimal number of hours. Let's see, did we skip the pos mod? We skipped the pos mod. I think that should do it. I do have better documentation for a lot of these, like for UT from time back here, for example. Oh no, I missed a line. One of the nice things, like code will line this up for you very nicely. Let's find an example. Here's a useful one document, right? Slash star star, bam. We'll expand that for JSTalk automatically. In this case, I already have some. So there are tools for sort of using that to define formally an interface that you can do quasi type checking with, which is pretty nice. I find this is good enough for a quick single file module, but you can if you want. Okay, so this is the contents of our module, and now we can get to testing. You probably saw that I had included Jasmine earlier on, so that is a pretty nice tool if I don't make typos, which I will always make typos. So this will be imported and evaluated when we do like yarn run test, right? And we'll define how that's done in a package later on. So we'll import directly from Next.mjs. And then what we can do is export mapping of can this module be tested, for example. And then each value in that key value pair will be a function that contains an assertion. So just as a software engineering practice here, I find it helps to, first off, you want to have like a test for each function, right? Or at least one. But it's also possible to go too far. Roughly speaking, if you have more lines of code for your test than you do for like this single module approach, at least, you might want to think about ways to consolidate that. The other comment is like, if you go through this text, especially since there's other algorithms cited or any other textbook you're implementing things from, you have a test suite here, right? You have all the, like here's, the example where he walks through end to end what the frame transformation is for Mars and Venus at a particular point in time, or Earth and Mars. And then each substitute, each algorithm within the algorithm, looking for a word, losing it. Each other algorithm that is used also has like multiple exercises and things. So I find it actually helps to go through a textbook and use that to define your test suite, as well as a few other reference cases where like, okay, things that are a little bit less, formally structured in textbook, like, did you get the rotation for the linear algebra helpers, right? Rotation matrices defined correctly. Or did you mix up the vector rotation versus the frame transformation directions? That kind of thing. Like, let's see. So most of these are examples. So you can say, can we reproduce this example or part of this example, like how that variable is computed, depending on how complex the algorithm is. So you can compute mean anomaly. Can we get true anomaly? Where's the rotation examples? Okay, yeah. So can we get a frame transformation about X versus can we rotate a vector about X, right? So this is a really good way to make sure you're not mixing it up, is making sure these things are included in your unit tests. Okay, there we go. We have some unit tests. Obviously, I wrote these beforehand. And then the last interesting part here is the actual package functions. So let's go into our package JSON here. We haven't defined much yet. So let's see that we need type module or node will complain. The nice thing about ES6 approaches for single file modules, by the way, you can use this directly in the browser. You can also pack it with Vite, of course, and you can run unit tests against it in Node, right? And it's all consistent environments. Thank goodness we're not living, was it 10 years ago, 15 years ago? So we're going to have some crazy scripts here. Just warning, these are going to look pretty weird. We're going to have a docs pass, a tests pass, and a coverage pass. So what these basically are going to do is, so you don't have like, dot files spread all over the project. These behaviors define the manner in which the configuration can be extracted from the package definition and then used to invoke those particular actions with specific frameworks. So let's take the docs pass, for example. It gets the package, it extracts this key that we're going to define for the JS configuration. Gets certain values from like the package definition for the name, etc. It's then going to write that out to a JS doc that will add to gitignore, so there's no redundant definition of how that's done. It's going to use the README to pass to JS doc to build the documentation using this template, right? And that's all defined within the package script. So now if we take that, what is the contents of that JS doc, right? And obviously this only works so long as you either know how to cast it from a string or interpret it from a string value, or in the case, if it has a JSON configuration, you can just include the JSON right out directly. Similar for Jasmine, although we actually need to define a runner for Jasmine. So this is a script that says get this reporter from the Jasmine package, grab the index. So that's what we're going to evaluate. From tests, we're going to go through each entry in that mapping that we exported, right? And we're going to say that that test, like the description of the test, can be tested. And then there's the function that's going to test. We also need a specific configuration for Jasmine. So again, that's just JSON, and then something similar for C8 coverage. So similar approach, right? Including for coverage, we take that configuration, we write it out, and then we run it directly against that configuration. So these are all self-contained now. So if we go here, let's say, first we'll need yarn install development dependencies. Oh, we already did that. So yarn run docs. Will it run the first time? No, it won't. How much fun is that? But we can see, right, JS doc conf. Bow, 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 bow. You don't want to track that, right? Okay. So what did I mess up here? UDF. So that's README. Oh, we didn't add the README. That's enough now. And of course, I don't know, is it always the file names that I mess up? Okay, let's try it again. Insert. Oh, we need specific versions for this. There are compatibility issues, unfortunately, between versions that we did not capture here. I'm just going to go ahead and C8, 7.12. Fudoc, if I remember correctly, Fudoc is the problem child. Jasmine 4.4, Jasmine reporters, 5. Honestly, the rest of these would probably be fine, but I know this works. Would have been a great reason to skip the yarn lock too. Go away. Gigantic node modules piece of. Oh boy. Yeah, that is a problem, isn't it? Thanks, code. Not only is it gigantic, code keeps a file lock on dependencies. All right, I promise we're just about done. I just want to show these. Ah, screw you, PowerShell. Oh, well. Hey, there we go. In our case, that went to an out folder that we would also want to add to get and ignore, of course. But you can see how easy these would be to add to CI once you have them, right? Index, bonk. Hey, look at that. We didn't document everything, of course. JSTalk is pretty nice. The Fudoc template is pretty nice. There you can see there's a reason I kept using it even with compatibility issues. All right. Yarn. That's now for the real. Yep. I knew there would be something. All right, let's see first. We can verify, of course. We can just, oh yeah, that was written out correctly. Oh yeah, that's going to run correctly. Unit results. Anything else? Sorry. Okay. So what happened here? Thank goodness for tests, right? Can it replicate? Actually, it can. 36H. I must have found that differently in the implementation. Okay. What else we got? Thank goodness for tests. 55. We called this Q0, DQ, and T0 just to be consistent. 59. Okay. A mod B. Our pause mod, say 64. U is a constant. I don't know why that didn't transcribe. That should have transcribed. That's strange. Ah, yes, because I had default arguments for these. Just in case, right? You can reuse this for Earth or any other planet. We're going to default to the sun here. In fact, I think I had done that in several other places too. What? That was angular momentum, RPW. Yeah, I've done that too. And I've done it in V as well. So what else did we miss? I can run. That's it. Okay, so that should be. Is that enough? Nope. A few more. 297. Capitalization probably. No. It's not defined. What are you talking about? Where's this defined? Ah. Kilometers per second squared, not kilometers squared per second. R cross V. No, that's wrong. It's actually kilometers squared per second. Let's fix that. Or are we going to mess up too many other things since I pasted implementation? We're going to mess up too many other things. 200. Let's see. Just right inside. That's how we define that. All right. Beautiful tests. Let's take, I don't know, should we take an example? Dang, what are we at? 50 minutes? No, that's enough for now. Okay, so what else do we want to look at here? At this point, this is entirely self-contained. This is entirely, like if you have npm.js credentials up, you can what was it? Publish or yarn publish, depending on how you have that set up in your system. And you'd be able to then go install this and use it in other projects. So this is at the point now where we can include this as a dependency in part 3 when we go back and revisit the dev challenge that's far too late to turn in. And use that to compute the positions of our planets. So that will be either next time or after dynamics, depending on how much time I have to prep for either one. Hope you learned something. This stuff is kind of fun for me. I hope it was at least marginally entertaining for you. Take care.